Okay, so welcome back. As promised, we will first continue and complete the Wittgenstein lower bound, which was an improvement on the Conlon further lower bound that we saw last time. And, well, hopefully after that we can also discuss some results on upper bound techniques, various ideas that have been used over the years, over the decades, to prove results. Well, in part, there's historical interest, what mathematical ideas have been used in these contexts. And in part, it will be useful to discuss the sort of book ideas and the book algorithm from the paper last year. Even though that doesn't generalize so well to multicolored, it's useful to see it again, to remember the basic idea, because even though the new paper is different in many ways, there's enough similarities, there's enough relations that somehow it's good to have that in mind. Right, but as I say, let's start by giving the Wittgenstein lower bound on multicolor Ramsey numbers. And it's similar in some ways to the Conlon-Ferber idea, because again, remember we had V being sort of the set of even layers in Z2 to the D. Well, we're actually using this for Z2 to K, where K is the size of the clique we're avoiding. And remember we said a subset is totally isotropic. It's just a fancy name for all of the inner products are even. So A was, let's call it TI, it's just a funny name, totally isotropic, whatever. If all pairs in A have inner product 0. Of course, this is over Z2, right? And it corresponds, we think of them as sets instead of vectors, to the sets all having even size and all of the intersections. So one difference with Wittgenstein's approach compared to Conlon-Ferber is, well, it works particularly better when you're doing more colours. Remember, we proved with Conlon-Ferber in the case of 3 colours, give a lower bound of the 3-colour Ramsey number. Well, when we just recall it, we proved it was the 3-colour Ramsey number for K was at least 2 to the 7/8 K. I think we just did minus a constant. You could put minus below K. And the Wittgenstein will work better if it's about more colours. I think when it's about 4 or 5, 6 colours and so on, it's already doing better than the Conlon-Ferber bounds. The Conlon-Ferber bounds, you can obviously, this is one case, you can also get their 4-colour result, and then you can apply that Atlas products observation. For example, R of 6 is at least the square of R of 3. Well, basically that, right? It gives you -1s, basically. But Wittgenstein gives a better lower bound than Conlon-Ferber, or even Conlon-Ferber when you use the added trick as well. So let's maybe just state his result, and then we can discuss a little more what we need to do. So this is theorem. I'm giving the numbers, I guess it's 1.4. Wittgenstein. I'll show this a bit bigger. They'll put up there. Theorem 1.4. Wittgenstein 2021. And for all R of these 3, if you're looking at the diagonal multicolor Ramsey number, this is R colors, and you think about cliques of size K, this is at least 2 to the 3 RK over 8 minus K over 4 up to lower order terms, so minus K. So this is the bound we will prove. You can see actually for R equals 3, it gives the same as Conlon-Ferber, basically because it's the same idea. But it extends very nicely to more colours. Before we launch into the proof, let's just say, I'll just say very quickly an idea. Going back to this sort of discussion, Colin further defined, let's look at the even layers within the cube, and remember what they did. We said we colour pairs green if the inner product is 1, if xy is inner product 1, that's wrong black pen. And we colour it randomly red or blue. We'll just get sticky or something. Colour it randomly red or blue if the inner product is 0. That was the idea behind the column and further lower band. But one of the things you did after that, you realised that if you kept all the vertices, you would still have lots of red and blue cliques. So we zoomed into a random subset of this size. Now, zooming into a random subset is sort of saying, okay, I actually have fewer vertices in my construction. The band I want to prove has fewer vertices than this 2 to the d, or 2 to the p minus 1. So I can take a subset. You'll see, if you look at Vickerson, when you put R, I don't know, 4 or 5 or something, soon this will get bigger than 2 to the k. So you want an example on more vertices than the 2 to the k or 2 to the k minus 1 you'll have available. But you can still do the same idea of basically thinking of sending your vertices you really care about by some random function into z2 to the d, z2 to the k, and colouring them with like a green or something if they have inner product 1. Because looking at all the pairs with inner product 1 is this very nice graph where you know already you won't get any cliques of size k by that kind of odd town dimensional argument we did last time. And so Vickerson kind of wants to use that structure, but not just once, but many times. So I've started doing a big sketch. I was only going to do a little bit of a sketch, but you start doing a sketch and kind of get carried away. So in a way, this is a graph G. We can even define it, and then we'll know already in the proof what we're talking about. Define G, a graph on vertex set V. This is the set of even pairs, or even vectors in Z to D, those vectors with an even number of ones, by you have an edge in G if X, well, the edges are the set of XY within a product Y. And we know G does not contain any clique of size K. We saw that last time. And I guess what we're going to use, the property we're going to use, is that if you do any blow up of G, so a blow up of G, a blow up is when you replace each vertex by a set of vertices and each edge by a complete bipartite between those sets. A blow up of G also contains no KK. So then you could take, if you're doing Vickerson with like R is 5, so you have suddenly more colours, right? And if you have more colours you can use, maybe I'll still keep 2 for the end to do the random colouring, but I have like 3 colours free that I could use. And what I do is I do a blow up of G and I plonk it down on the vertex set. I know that pen isn't very good, but anyway, there's a picture there. And then I do another random positioning of another copy of G on top of it, and I colour all those edges in the second colour. So it's like having a bunch of green graphs. In the first construction, we had this one green graph, which uses very cleverly this property of if you have inner product 1 in Z2 to K, you have no clique size K. We want to use that many times on the same vertex. This is really the idea that's happening inside Vickerson's proof. when we actually write the proof, we'll write it in terms of random functions. You map the n vertices into the graph. But what's really happening is this. Because the set of vertices that are mapped to the same points behave in the same way with respect to them. Okay, so let's maybe stop sketching and start doing something. And one thing we will note, this is going to be things as follows from a result of last lecture as well, is a bound. It's going to be very important to have a bound on how many of these totally isotropic sets of a certain cardinality there are. Okay, so if you like, how many sets are there where inside all the inner products is zero? We proved bounds for that last time, and let's just note the consequence of the bounds we proved. So T I K, I'll just go off K. I mean, I should probably put more in this notation, but this is what we need. Let it be the number of totally isotropic sets contained, so A contained in Z2. So actually, I'm going to use K twice. Z2 is the K, and of cardinality at most K. Okay. So this will be what we actually will need at some point in the proof. And we have a bound on that simply by using the last time we proved bounds on the number of totally isotropic sets of size exactly L for any L up to K. And then you just sum those up. Okay. So T I K is at most. I mean, you could put in the summations from last time. KL minus L choose 2 plus 2. You do this from L to 1 up to K over 2. And then in the rest, K over 2 plus 1 up to K, and you have 2 to the KL over 2 plus K squared over 8 plus K over 4 plus 1. But all that really matters is basically these are all increasing as L gets bigger. So the biggest term is when L equals K. And it's sort of a geometric type behavior as well. So the whole sum is the most constant times the largest term. So this is at most. And the largest term, you put L equals K, you get 5/8 of K squared, 5K squared over 8. And then I'll just put a little OK squared. I mean, it would be something smaller than that, but we just don't really. Actually, with this proof, I'm going to try and be better at just throwing away terms we don't care about. So a little OK squared. Good. So let's do a proof of Vickerson now. I should say it's Yuval Vickerson. I think his father's quite well known computer scientist. It's worth pointing out which one. He was a student with Jacob de Vos, I think. Yeah, great. Well, sort of established in his own right now as
Simon, quick question. So is this known asymptotically? Probably not, right? The totally isotropic sets number?
Oh, you mean, do you know exactly how many there are really? Probably, well, I guess, well, one answer is I wouldn't know exactly. I think there was some inefficiencies in the way we were bounding here. It's probably something that someone could do if they really can. I think it would be of this form probably. So I don't think it's probably not too much to win. I just realised we didn't turn on the lights. The light from outside. Would it be better? Is that better?
Yeah. Thanks.
Okay. I don't know if you get shadow. Anyway, so let's prove let's prove the Vickerson result then.
Just a question,
Okay.
I'm assuming something about K, is it even or?
Well, yeah, so I'll put, really, I think in the proof it will be useful, so thank you, because it's for some of the algebraic properties it's useful. We should assume K is even. In a way, though, that doesn't hurt us, because, you know, if K is odd, then I guess K minus 1 is even, and the bound is basically identical, and the difference between the bounds would just be in the. Okay, thank you. The observation. Let's strangely what we're going to do. Our number of colours is R, but let's write R as M plus 2, because actually there'll be M colours that we use for this funny blow-up idea, random functions idea, and there'll be 2 colours we keep for the end to randomly colour whatever is left. And we shall prove that for if n is, now it's going to be 2 to the 3mk over 8 plus k over 2. Instead of a little lower term, I'll put minus epsilon k. And then, of course, whatever you prove will work for any epsilon bigger than 0, if you low k. That there exists, well, for all k sufficiently large, k is sufficiently large, there exists a m plus 2 colouring with no monochromatic AK. And I know it's slightly annoying that the statement was with R, and now I'm saying I'm proving something with M, but it is exactly the same statement, right? If you have R means 3, you can write M plus 2, and you can just check substituting in M is R minus 2, it is giving you the right result. So let's get to the Vickerson's real idea. It's it's interesting, we have this V, you know, the even layers instead of K. In a way, that isn't really our vertex set. That's something where we have already defined a graph there. We define that graph G, but we're going to have use just 1 up to n as a vertex set, but you're going to map those vertices into the other set and use what happens there to decide the colouring back in your graph. Okay. And we're going to do that many times, because we're going to try many times to colour. So what do? You let F1, well, let's say let Fi from 1 up to n, brackets n, into V, be random functions in the sense of uniformly random functions, and this is for I1 up to n. And now I need to tell you how these are going to relate to the colouring. So here's the rules for colouring. Colour, well, let's start with if. But I don't know what to start with. Let's say given. Given U and V in N, if there exists I, if for one of these random functions, the image of UV, so Fi of U, Fi of V, is an edge of G, if you ever land on an edge of G, then I will colour UV with that number, with that colour I, which is like, basically, the things you colour with colour I are exactly like in that sketch picture. You're going to colour anything which is in this blow-up of a copy of G. So with colour I, there's maybe a slight problem here in that something might be coloured more than once. If you want to say the least such I, so if you're trying to color it more than one time, use the least I. And otherwise, there might be some pairs left that still aren't colored at all. You do randomly with one of the last two colors, n+1 or n+2. And the first thing we can say immediately by our observation before we started is there is no KK in, well, previously, last time, no KK in green, but we said there's no KK in graph G, there's no KK in any blow-up of G, and if you think about it a little bit, you'll see the things colored I are contained in a blow-up of the graph G. So there's no cleave size K in any color I in 1 up to M. So the only thing we need to do is bound the number of cleaves. Well, we want to show there's no cleaves in colors n+1 or n+2. And how would we do that? Well, first moment, so we'll do an expected value calculation, show the expected number of cleaves in one of the other colors is small, and therefore it's possible to color and avoid any cleaves of size K. So let's think, what does it mean first for a set to be a cleave in the same color n+1? Okay. How can a set A contained in N be a cleave or a KK? Let's assume A has size K in color n+1. So there's quite a few things have to happen. The first thing, I suppose, is you don't have any of these other colors coloring any edge of A. Right? If one of these colors colors one edge in A, then already you're not going to use this n+1. Remember, n+1, n+2 are these colors you kept for the end if you didn't manage to color the other colors. So you need all of the other colors to sort of fail on the whole set. And what does that mean? It means that the image of A under this function is actually an independent set in the graph G. Because if you map, look at the image of A and there's any pair that's joined by an edge of G, then you can use that color. So this is indep in G for all I is 1 up to M. And some discussion about the air conditioning here, which so what does it mean to be independent in G? Remember, a pair is joined in G if the inner product is 1. So to be independent, it means all the inner products are 0. It's lovely Z2 to the n, but it's only 2 values of the inner product. It's a nice fact. So to be independent in G is exactly the same as to be one of these totally isotropic sets. So I could change independent in G to is totally isotropic. And even if you're successful in this first set, your set A is totally isotropic, the image of it is totally isotropic for every 1 up to n, you still need to be coloured all the same colour. So all the edges are coloured red. Or sorry, I'm thinking of it as red. Anyway, it's n+1. When you do the random colour. So obviously the second part we already know very well. If you say you got to this point, the second thing has probability 2 to the minus k choose 2. Right? Because A would be a set of size k, and covering all the pairs, same color as 2 to the minus k choose 2. But what we don't know a priori is how many A such that the first thing happens, right? How many A is such that in every one of these functions, they're totally isotropic. So let's think, what's the probability that A has this first property? So you take, say, a random set of K, well, you fix K vertices in N, what's the probability this occurs? So for this to occur, there must be a totally isotropic set of size at most K. So Fi of A is totally isotropic. You know, it's maps of these pairs that all have inner product 0. This is basically if and only if you're basically saying there exists a totally isotropic set T contained in V, such that the image of Fi of A is contained in T. Right? And what's the probability of that? You fix the T, you have the probability Fi of A is contained in T. Well, each vertex independently goes somewhere. What's probability goes to a particular, in a particular set T, it's size of T over the size of V. And you have to do all K times, because you have K elements in it. And this is like, and the totally isotropic set has to have cardinality in most K, just because you're mapping K things in, so that, you know, it has to be a totally isotropic set. So this is at most K over what? 2 to the K minus 1, all to the K. And so the term that matters here is a 2 to the minus K squared. And we'll just say classically low K squared.
Why most K?
Right, because this only has K elements, right? So if I map a K element set and it's contained in a totally isotropic set, then there also exists a totally isotropic set of just K elements, which also contains it, which is like the intersection. So you can insist that there will exist a small one. And then we get this bound. So then what's the probability that if you don't fix T, that this is totally isotropic, all inner products at 0? Well, it's at most the number of choices of T times this probability. But we already have it up here. The number of choices of a set T with these properties is at most 2 to the 5/8 K squared. So at most, by union bound, 2 to the 5/8 K squared minus K squared. So many of low K squareds, whatever. Anyway, the message is it's 2 to the minus 3/8 K squared. That's low K squared. Good? Right. That was for one of these random functions, but all of the random functions are independent. So what's the probability that the same thing happens for all I is 1 up to n? Well, it's just this to the m, so 3m K squared over 8 plus K squared. So it's already looking quite unlikely. We don't know exactly what this means in terms of all our bounds, maybe, but it's already saying it's fairly unlikely this first thing happens. And now it's a single calculation and will be done. So maybe let's, as usual, we have a random variable to count the bad things that happen. So let x be number of monochromatic KK. We've already said we will only find them in colors m+1 and m+2. And then let's do the expected value calculation. You need to think of any set in A this could occur. So you do a union bound over the possible sets in A of size K. I mean, I've already put in inequality. I don't know. You've got n choose K then, the choice of A. And then the probability that A really gives you a clique. Well, first, this needs to happen, which has probability at most 2 to the minus 3m K squared over A plus no K squared. And then you need something else to happen, which is the random coloring gives you all the same color, which is 2 to the minus K squared over 2 plus this low. Right, it's 2 to the minus K choose 2, but we're ignoring all those smaller terms. Right, and this guy, we're just going to use this at most n to the K. We don't even need to be too precise. And so big brackets, n. So I'll put K in the power of the big brackets, right? So this is n to the K. K's up there. This is 2 to the minus 3nk over 8 minus K of 2 plus little o K, which is low K now. And I know it's difficult, we've already rubbed off what n is, but n was basically exactly sort of the positive version of this, 2 to the 3nk over 8 plus K over 2 and minus epsilon K. So if you put in the value we had of n, this is at most 2 to the minus epsilon K squared plus K squared. In other words, it's just something that goes to 0. So it really does work. It really is expected value going to 0 that the expected number of monochromatic cliques. What happened? Remember that changed when we did this change from R to M. Because R was M plus 2, we took 2 more colours. And that difference is like a 3/4. So this is the slight change we did at that moment. But yeah, it basically gives this.
Okay.
So, and a standard probabilistic combinatorial saying, if it's reverted against 0, it's very probable that you in particular have an example where the coloring works. Good. So that is the proof of Ferguson's bound.
Yeah, I was watching the Zoom. Can you just remember how you color the first M colors?
Yes, the first M colors, we took M different random functions into basically the example from last time, and we colored with color I if in the I function you had inner product 1. So you basically took the green graph from last time and you used it lots and lots of times for each of those colors. I is 1 up to M. Or effectively a blow up.
And you don't have a KK by the same reason.
Yeah, and you don't have a KK, it's exactly the same reason. And then the only colours, only edges to worry about are the edges to the left, and you colour those randomly with 2 more colours. And then we did the calculation, and this is what it gives. So it's a nice, as I say, I think it's really one of the most important things in probabilistic combinatorics and, well, Ramsey stuff and lots of other things, extreme, to understand the interaction between structure and randomness, between algebraic instructions and doing some random afterwards. Yeah, there's a lot of interesting stuff to be done there, I think. Although, what I'm about to do is to contradict myself. I will immediately contradict myself by saying that, like a year afterwards, I think, or something, Selwyn, we put the results up when we had the slides last time, slightly improved on this result by actually making things more random, in that instead of this very structural graph coming from inner products, what he did is he used a random graph with density slightly less than a half, and he could ensure there were no cliques there, and he used that instead of this algebraic idea. I think that the rest of the proof in a sense is similar to what we did here. Really. It's just sort of using these random maps, but into a slightly different graph. So anyway, using constructions plus randomness, using randomness plus randomness, combining these things in different orders than we thought of doing before, I think there's always still potential to improve these things. I mean, we're going to get on soon to the upper bounds, but let me just mention something related to the upper bounds already. We already mentioned the first, well, the end separate upper bound for 3 colours. I mean, for 3 colours, you may think for 2 colours, we have a lot of space between the lower and upper bounds we know. For 3 colours, okay, we have 2 to the 7 k over 8. So still less than 2 to the k, right? It's getting close. And the upper bound's like 27 to the k. This feels like a big difference. And then maybe, as we say, in the latter part of the course, we'll see how you can improve this, but it's very kind of small exponential improvement. So it's still a huge gap, really. Our understanding is pretty limited. Magic has occurred again, the boards since we've been for no reason. So that sort of completes what we wanted to say about lower bounds. Let's go on to upper bounds. So, as I say, today we'll focus more on what's known in the 2-colour case. That might be familiar to some of you, but it's good to sort of see a revision of these arguments just to kind of make sure we have them ready in our minds, ready to go on to think about the variations on it for more colours. And yeah, and there's nice ideas here, and there's nice things to think about. So we obviously start with Ramsey, who showed that for any K and L, RKL is finite, and we already mentioned Edwards Separate proved the first effective upper bound, which I'm going to say is K plus L choose L, or K plus L choose K. Okay, you can have -1s and stuff, but care, and that's less than 4 to the K. Sorry, when you do the diagonal, when you do KK, it's less than 4 to the K. So when you go on the diagonal, in particular, KK is at most 2K choose K is less than 4 to the K. The first major improvement on this, or at least published improvements, because it's possible that Rowell had something before, but the first published improvement was Thomason in 1888, was to improve this by a factor of root k, so to most k to the -1/2 plus below 1, times this 2k choose k upper bound of Edwards Separate. So that would be maybe the well, we'll go into the slides in a minute, and I'll give a brief description of some of the ideas in Thomason's bound. And a very brief, well, too brief, but very brief discussion of how that changes if you go on to the next people, Condon and then Sarth, who improved on it. I'm sort of doing a version of this is pretty similar to what I just took from David Condon's notes. Anyway, well, maybe I'll put them in the description and so on. But Thomason's argument relies on sort of, well, I mean, he sort of thought through these things. He sort of thought a lot about quasi-randomness. He actually had the plan to go as far, well, the furthest we managed to go start with quasi-randomness techniques is to win e to the minus constant log k squared. And actually, Andrew Thomason said in the 1980s, he already had some like sketch proof of how to use quasi-randomness to maybe get as far as this. The problem was, as many of us know from our lives, sketch proofs do not always turn into proofs, and the technical details got a bit out of hand. And well, first Conlon, who proved a similar bound, and then Saar managed to push it a lot further. They were great sort of technical successes in. I think obviously they're huge successes individually in terms of being able to do it. I think they're also related to, over time, the vocabulary in the community about these things grows, right? You learn more ideas, you have more vocabulary about how to think through things. So maybe there were some things in that sense that maybe helped it become more possible as you went on. Then it would have been more of a challenge like in the 80s. Good. So let's mention a formula which Thomason's method uses, which is the Goodman formula. Maybe you've already heard of it. And it basically says if you colour a complete graph with two colours, and you're interested in the number of monochromatic triangles, then you can actually determine that exactly just from the degrees. I mean, you can just state in terms of degrees in a graph, and then you just want the number of triangles in the graph or the complements. But I'll state in terms of a two colouring because we're interested in two colours. So let Kn be red, blue coloured, and let, I'll just do a triangle be the number of monochromatic triangles. This is triangles. Then you have an exact formula for the number of monochromatic triangles in terms of degrees. So in fact, twice the number of monochromatic triangles is the sum of the red degrees, choose 2, plus blue degrees, choose 2, minus n, choose 3. So the sum here is always over all vertices of the graph. And it's not difficult to justify why proof. So the red sum, the sum of all the red degrees, choose 2. You can think of all the triples that you count here, because you count a vertex having 2 distinct red neighbours. And the third edge could either be red or blue. If the third edge is red, then the way you count is 3 times this sum, because you're counting from the point of view of all the 3 vertices. If it's red, red, blue, you only count it once. So this counts red triangles 3 times and red, red, blue once. And the other sum, with blue, obviously symmetrically, counts blue, blue, red once, and blue, blue, blue 3 times. Okay. Well, now, if we subtract the minus n choose 3, counts all of these types as minus 1. Right? It counts all triangles exactly once. So when you add up these 3 terms, what do? You count red triangles twice, you count blue triangles twice, and you count everyone else 0 times. So that's kind of cool. It's pretty cool. And it turns out this is very useful, and well, probably for many things, but in particular with Thomason's ideas as well, in that enables you to get improvement, it's root K on the random. So I think what I'll do now is I'll switch over to the slides for a little while. We can go through things on there, and at the end, maybe we'll come back if we have time, to the boards and discuss some of the challenges and some of the ways we are thinking about generalizing and what are the challenges to generalizing small colours. Right, but shall I? Yeah, I'll pause the video while I mess around. Okay, so now we are on the slides. Funny AI image again. If you tell it to do a graph coloring with paints, then it comes up with something a bit crazy. Now, so yeah, as I say, some of these slides have kind of come from various. The slides are. Oh yeah. Yeah, some of these slides are talks I've given over the little while. So anyway, I think they're kind of relevant. So let's talk about upper bounds. As we've already mentioned, we have Ramsey showing the upper bound is finite. Probably these slides. End of second edge giving the first effective upper bound. So in the diagonal case, it'd be 2k choose k, which is at most 40k. And these are the improvements. Yes, these are the improvements that have happened since. Well, I'm actually going to have two groups. So one group here, we'll get into another group in a minute. So these are the improvements, basically, that implement Thomason's sort of strategy from the 1980s to use quasi-randomness in some way to enable you to improve. And as I say, you know, Condon and then SAR's improvements were huge, technical challenges. And I'll say a little bit about them. I won't be able to say nearly as much as I ought to. It's also SAR, I think, back in 2020 or something, recorded a video or some seminar that's online. If you put SAR Ramsey, you'll also find it. So you can see a nice seminar on it. So Condon got an improvement of constant log k squared here in the exponent, over log k, and SAR managed to get rid of the log k by doing details even more carefully. And nice ideas about putting it in the language of graph bonds. And it really is like the limit of the method. So it's definitely very interesting to know when you have a method you're applying it to a problem, and a method that even has many other applications in graph theory. I suppose quasi-randomness is also interesting in quasi-random groups, quasi-random permutations, lots of other settings. It's nice to know when you push a method as far as it can go. Yeah, I mean, I kind of get confused about, originally I think put the archive dates and then these are the journal dates. And then when I put the other dates, there'll be archive dates again. So, it's a bit confused. Yeah, those are the, so the other group we'll talk about is getting an exponential increase, which happened last year. So we'll talk about this a bit later. Our group, and then they managed to optimize lots of the ways in which the ideas were implemented. In fact, adapted it in interesting ways as well. I'll say their names later. It's a group of McGill, and they got an upper bound of 3.8. Okay, good. So the silly bar Zoom. The end of separation. So I know it's familiar to you all, but it's worth saying because it's the context for everything that happens. The end of separation bound is an induction. You basically use the fact you have this relation for this identity for binomial coefficients, and you use a relation of Ramsey numbers compared to ones that like one down in the same style. So we're going to prove RKL is at most, I guess you have this. So if you want to prove the upper bound K plus L choose L, then you know the number of vertices you have. You need to show you can find red k, k, or blue k, l. The number of vertices you have is the sum of these two binomial coefficients. And you pick a vertex. Of course, the rest only has size this minus 1, because you've already taken one guy out. But even so, one of the two has to be at least the value, the corresponding coefficient, because otherwise you have the sum minus 2, right? So either in red you have at least this, or in blue you have at least this. And in either case, you just by induction have, let's say in the red case, the red neighborhood would have at least r k minus 1 L vertices. And so you can either find the k minus 1 clique in red, which together the red vertex gives you k clique, or you find a blue L clique in here, and you're just done. So that's the end of Sekresh bounds. Right, so this is about how do we improve on that? How do we I'm just going to pause. Okay. Good. Right, so let's see previous improvements, in particular, say Thomason's improvement on the upper bound. And you could think of it as wanting to do the end of Sekresh argument, but thinking, well, maybe if I could do more red steps at a time, that would somehow be more efficient. Remember, especially if you think of the diagonal case, when k and L are equal, you have RKK. Basically, you want to go into the neighborhood which is larger. And if both are around a half, you know, one's a little bit above a half, you want to go into that neighborhood, right? Red neighborhood is half, do red step. We'll call it a red step. But what would be ideal is to do like quite a few red steps. If you can do quite a few and really just be losing a factor of 2 each time. If you can just lose the factor of 2 each time, but do a large number of steps at once, everything just works a bit better with the calculations, and you just get a slightly better bound. Actually, when you think about exponential improvements, if you manage to do a linear number in k, like k over a million red steps in a row, and just lose a factor of 2 for each one, then you get an exponential improvement. So, but to begin with, you just think about doing one, right? Goodman's formula, which we have just proved. And it has a certain corollary. Basically, now you have the formula, you can say, well, how would you minimize this function on the right? How would you have as few monochromatic triangles as possible? Well, when you have convex functions, you minimize them by making them all equal, right? And so you minimize this by putting all the red degrees and all the blue degrees equal, and I guess n minus 1 over 2 or something like that, depends on the parity. But anyway, if you go through and do the calculation, you can show you have at least this many monochromatic triangles. Corollary. There exists an edge which is in at least n minus 5 over 4 monochromatic triangles. Well, how do we know this? There are n choose 2 edges. You know how many edges there are. And you have a lower bound on monochromatic triangles. So you just divide this by n minus 1. You think just divide by n choose 2, but then I think you need to divide by 3 for the number of, you count each pair 3 times. Okay. Anyway, this is the number of monochromatic triangles you can guarantee on a single edge, which kind of makes sense, right? Or, you know, it's pretty good, but it's like if 2 endpoints both had joined in red and blue equally, you know, had degrees about n over 2. This would be roughly the order you'd expect if it was random, right? You'd say I have a pair, and they each join randomly to the rest. You'd expect to get n minus 2 over 4 or something. And you're saying you can basically guarantee that. And as a corollary, from the diagonal, you can actually do 2 steps. So it's similar to the bound we had with, well, if you just open the diagonal, the previous bound would be your most RK, or twice RK K minus 1 by the symmetry. So here, you can now get 4 times the 2-step version. There sneaks in this +2 when you do the calculation that comes to the -5. It's just a small detail, easily checked. But when you do it, when you think about it, you can see what this is giving you relative to 2k choose k, which is the bound you would have got if you just did 1 step. Just do 1 step, you get this bound. If you look at this, you win a factor which is like 1/2k, basically. So you win a factor, or like 1 minus 1/2k, right? You get to multiply what you achieve by this. Now, the first thing you should think is this is very unimpressive. This is not a big factor to be winning. However, maybe you can kind of do the same thing again from where you land and improve that by this factor as well. And maybe you carry on doing it everywhere and you do it for like k steps. I say k, actually, you can do k steps. I say k over 2 steps. I think you do k times anyway. And you would win actually like a constant factor, right? Because you have here, and this should be k, I think you do k times anyway. You do it like k times, and you win this factor k times, and then you could win a constant factor, like e to the minus 1/2. Yeah, but maybe that's, yeah, no, you're right. Yes, maybe it's k over 2, yeah. So if you do k over 2 times, then the total, like the sum of these, would go down by k. And it may be that you go far off the diagonal as you're doing this process, but actually, if you go further off the diagonal, you tend to get better bounds. You tend to be happy, right? Everyone tends to be better. That's kind of the whole idea of the proof where we try and go off the diagonal. And still, the worst case is where you still have roughly the same number in red and blue to get. So in the worst case, you're kind of comparing to our k over 2 choose, or k over 2 comma k over 2. But that you can still improve by another factor. But by the time you think about our k over 2, k over 2, by this same argument, you're winning a factor which is like 1 minus 1 over k, because the k in quotes will now be k over 2. But then doing k over 4 steps, you'll win a factor of 1 minus 1 over k to k over 4. Right? In other words, going from kk down to k over 2, k over 2, you win a constant factor. From k over 2 down to k over 4, you win a constant factor. Well, you can do this log k times. So if you do that log k times, then you win a polynomial. So that's a sketch of how you can use the Goodman, the inequality for the number of monochromatic triangles, to give you a tiny win in 1 step, but how you can turn that into a polynomial win on the actual Ramsey upper bound. If you do this carefully, then you can get something like Thomason's bound, which is like a root k. So what's the natural way to try and generalize that if you want to go further? Well, you could try and do m steps at once instead of 2 steps at once. What's the first thing that falls apart? The first thing that falls apart is that you don't have Goodman anymore. Goodman guaranteed us a lower bound on the number of monochromatic triangles in any coloring. And that's just not true anymore. There are colorings with fewer K4s, monochromatic K4s, than you would think. This is actually Thomason as well, who first proved this. Later, the constant has been improved. So that direct approach is completely closed to us, it won't work. If you could do, let's just dream, if you could do m steps at once, and you kind of follow your intuition about how it will happen, you could sort of do 2 to the minus n times n, km plus 1s. You think about the term you win relative to the English-Sekresh argument, then each time you'd win a term like e to the minus n squared over k, you can do it k over m times k over 2m times before you go down to half as large, like k over 2, k over 2. And you win e to the minus constant n. In other words, in the time we were winning a constant, you now win e to the minus a constant times your sort of big step size. And if you iterate that log k times before, like k to k of 2, k of 2, k of 2, k of 4, k of 4, you win in total something like e to the minus a constant m log k. And this is exactly the approach which Conlon managed to push through up to log k over log k, and, well, even further by Saar, we managed to do it for m of order log k, which there's sort of good reasons to say that's really the limit of what the method can give. Now, what is the method? I didn't really go into the method, but the method is, you say, suppose I have this really clever colouring where I can't win this factor, I can't win a nice little factor, then I kind of know that colouring has to have at every vertex roughly the same number of reds and blues, because otherwise I could just win a factor even using the English-Sekresh step. I kind of know something about the properties of how many triangles contain every edge, right? Because otherwise I can use 2 steps and I can always already win a factor. And you can put this information together to basically give you quasi-randomness information. You can do things like say the number of C4s in a graph in each color is roughly what it should be. And there's lots of theory of quasi-randomness that says if you have that information, you know the count of all subgraphs should be roughly what it should be. If you don't know that stuff, it's kind of surprising, that statement. Chung, Graham, and Wilson published an article, it's around 1990 or something, which kind of said all these list of conditions turn out to be equivalent, and having the same number of C4s as a random graph is enough information to know that all your subgraph counts similar to a random graph, which is kind of weird. Yeah, and as I say, over time, maybe our technology, but also like obviously these guys worked really hard and had, you know, clever ideas in implementing it. They managed to show with this quasi-randomness you could understand the number of larger cliques, even from just that information. So can these methods handle multicolor? That's sort of the question we're going to get around to, because obviously the focus of them afterwards will be trying to get back to there. This is copy and pasted from David Condon's PhD thesis. Maybe I won't read it all, but it does say, this is the only chapter in his thesis without a multicolor generalization. And he explicitly points out some of the difficulties associated with generalizing the method to multicolor, including that you can't even immediately read off quasi-randomness conditions in the same way as you can in the 2-color case. And then even so, once you've got a type of structures you'd be counting might need to be more difficult than just like these large cliques. Even so, he expresses some optimism that it probably is possible to generalize these methods. But yeah, he hadn't got around to like really focusing on it. There are definitely problems with generalizing that approach to multicolor. Right, so let's mention the exponential improvements. And in one way, it's very similar because it's about trying to do many steps in the same color at once. I've got some people here. This is Marcelo, Rob, Julian, and myself. And then I put pictures of us in Carnival or Marcelo in the beach, just to make it a bit more, enjoyable and funny. Well, yeah, it's very different as well, but it does still have this basic idea, this idea of doing many steps at once. Now I'm simply calling it T, the number of verses you're doing at once. Now, this type of structure is in a graph is called a book for some reason. So what we might want to find is a book where we have a clique of size T, and then a large set of vertices which all join in red, say red, to that clique. And then we call that a red book. If you can do this in such a way that the set of vertices here is still at least R, K, K minus T, then you are done. Because either you find a blue clique of size K in here, and then you're done in blue, or you find a red clique of size K minus T in here, and together with the other side of the book, you're done. And, well, this is another observation. We spent years trying to do this argument directly from the diagonal and about the diagonal Ramsey numbers, but we found out it works better if you go off the diagonal. And off diagonal for us means you have K and L of the same order, probably, but L could be 100 times smaller. So think of that case. Actually, we're going to use gamma to denote L divided by K plus L. But it's kind of, if L is small, this is kind of similar to L over K. It's kind of, think of it, if L is 100 times smaller, it's like gamma is 1 over 100. One thing you can note is the upper bound is basically given by, well, this is a property of the binomial coefficient, that it's similar to gamma to the minus L, 1 minus gamma to the minus K, for this value gamma. This is the same as like 4 to the K in the diagonal case. Right? These things only differ by a polynomial factor. In fact, it's easy to prove this thing on the right is an upper bound for the Ramsey number, because you can just say, I'm going to take a red step if I have at least 1 minus gamma proportion of my neighbours in red, and I'll take a blue step if I have at least gamma proportion of my neighbours in blue. So if you it's kind of a variant of the Enrich-Sekresh. If you are less careful with doing the induction, and you just say, I'm going to do red if I'm at least this, or blue if I'm at least that, then you can also get these upper bounds. And we managed to improve the bound by an exponential factor in L, in the smaller of the two, e to the minus over 50, plus low k, if L is small compared to k, say L most 10. Yeah, we'll come back again and say actually that you can then use this to get to the diagonal, but somehow our method here in this paper works better far from the diagonal. So the Enrich-Sekresh argument, or at least a simplification of it, is just to say you do red if you have at least a half in red, blue if you have at least a half in blue. That's when you're going from the diagonal, right? Another way to draw that is to say that really you're building up a red clique and a blue clique at the same time, and you're keeping track of the vertices that join correctly to both. And the number would be at least n 2 to the minus a minus b. And if you could just do red steps, then you'd have t elements in the book, and this would have size n 2 to the minus t if you could do red steps that actually worked just for the factor of 2. And then pretty quickly you'd win an exponential factor. If you do the off-diagonal version, as I said, you can do red if you're at least 1 minus gamma, and blue if you're at least gamma proportion, from the point of view of the neighbour, and you repeat it, and the number of vertices you still have, which join correctly to both, should behave like that. So what we're trying to do is we kind of want to, in some sense you think, I want to force myself to do more red steps, right? But that doesn't really make sense, because you always have to think the rest of the colouring you have, you don't have any control over what the colouring is, so you have to imagine your enemy has put the worst possible thing there. It could all be blue. The version I'm going to give in the slides, because we don't really want to go over the details of this whole proof. I would say maybe I'll put in the description of the video, like Rob's mini course. Rob did a whole mini course on this proof, or even reading the first couple of sections, few sections of the article gives a nice sketch here. We'll give the story version here, just so we can think through some of the ideas. And I do this little trick of saying, let's start with a completely naive idea, which is to say, we want to force ourselves to do red steps, so just do red steps. For some reason, this comes in useful later, I'm going to think of these on the left-hand side, X being the reservoir, future verses to put in the book, and Y as like the book we're building. So what you could do in one step is always add V to A, and then restrict X, the candidate vertices for the future, to just the red neighbors of V, and restrict Y to just the red neighbors of V. And that's certainly a valid step. It could be a stupid step, because maybe everything in here is really blue. Maybe everything in X is really blue, and then in one step, the process ends. So to be a little bit less naive, in the left-hand side, you could sort of have an N or second-esh type approach, where if the vertex has a really big blue degree, you do a blue step, which you put in this blue cleat, which is joined to X blue. And if not, then you do a red step. And that's how you write it down. But it's basically saying that we're using gamma as a threshold for when a blue step is big. It's still not a great idea, though, because you could still lose. You want this Y to stay big. You want to build a big book. You want the Y to stay big. And it could be that this V you showed has very bad red degrees the other side. That's blue edges, the red edges the other side. So this could still be a very bad one. So what we should do is we should keep track of the red density between X and Y at all times. This should be like the fundamental thing we want to understand, the red density between the two sides, because this is what allows us to maybe pick a V with a good, good red neighbor as well on the other side. So you could say I want to do the previous argument, but with a vertex here which has a reasonable size red neighbor on the other side. I mean, technically, in that algorithm, we actually throw out versus V if they have a density much smaller than the average. So we kind of are maintaining it, so everyone would be. But it could still be a problem that over time, as you do many, many steps, to begin with, this is all working great, but over time, the red density between the two sides could go down. And then the fact that you get density P every step, or 1 minus, I guess you're close to 1 minus gamma, it turns out, this could go down, and then it's not so useful. And what does that problem look like? So this is the point where you actually can stare at something and say, well, we have a problem. How do we behave? So it could be that your red neighborhood of V on the left and the right are both big enough. They're both fine in themselves. But between them, you have less red than you would want. Which means if you do that red step, the density in red will fall. Now, this is the moment where it's useful we're actually in the off diagonal. We're in the off diagonal. In other words, looking for something much bigger in red than blue, let's say. So maybe in red we want K, in blue we want K over 100. That means that the general degree in red is about 100 times bigger, right? Because, if the degree of blue was reasonable, you could just do blue steps and you'd win a huge factor of red. So this red neighborhood I've drawn on the left is actually like 99% to the left. Okay. So if you have a disappointing neighborhood, few red edges here, but actually it's not too difficult to pick a V such as the red edges from its neighborhood to the left-hand side on average is okay. That's just sort of Cauchy-Schwarz. If on average it's supposed to be okay, so this 99% it's bad, then this 1% is doing very well, right? I mean, you could make jokes about the income distribution of Brazil or something, but anyway, If the 99% is not doing very well, and on average it's okay, then the 1% is doing very, very well. This is a very high red density, in other words. So what you do in this case is you actually say, okay, our big objective is to build this red book, but sometimes I'll just pause. I won't do my red step that I want to do. I'll do something completely different, which is just restrict X to here, restrict Y to here, and get that boost in density. So we'll call it a density boost step. And it's useful in a different way, right? It's not giving us a direct progression towards the book we want to create, but it's giving us something else that could be useful in the long run, higher density. However, there's obviously some trade-off about when this is worth doing, when it's not worth it. But that trade-off becomes much easier when you get this sort of multiple of 100, right? Because if this is just even a little bit disappointing, and this is much smaller, it needs to be much higher density to compensate. In particular, if the sparser meant you're less than p minus some alpha, then the denser means p plus this multiple of alpha, which is a bit like 1 over gamma. So it's a bit like 100 in this colloquial example, say. So, okay, it's a bit too technical to go through in details, but you can write down now your algorithm for how to do your choices. If you have good density in blue, you do a blue step. There's a technicality that actually we do it only when we can do a lot of blue steps at once, but it's a small kind of technicality. Otherwise, we want to do a red step, but we make a choice. We do the red step if the red density goes down just a little or doesn't go down. If it's going to go down too much, so we do the red step is only going to go down by most alpha. And if it's going to go down more than alpha, instead we do this density boost. There's still a problem. I mean, all this nice storytelling and sounding optimistic is great, but you know, there are some choices to be made. One of them is how much density do you accept to lose in each step? This alpha. So it could be that your enemy just gives you these little decreases in density every time, not too much, and you just do red steps all the way. But you want that at the end of the process, you're still only losing the same kind of factor each time that you did at the start. That's the whole idea. Like we were saying in the even in the Thomas argument, you want to use just half every time. You don't want to lose bigger factors every time because that just completely ruins all your maths. So in other words, you want the total density you lose to be pretty small. This notation sometimes used to be like little o, basically. So you kind of want alpha times the number of steps you're going to do to be little o1. On the other hand, we don't want, what's the opposite problem? The opposite problem is the enemy, your opponent, who makes up the coloring and shows it to you every time. You kind of have to assume they can do what they want, because if you just describe an algorithm, then at each step, you don't have control about what's shown to you, right? So your algorithm just can respond, and when you analyze it, you kind of have to assume at that moment the opponent comes up with the exact worst thing you didn't want to see, and you have to analyze what it does in that case. So what if your enemy just gives you these density boost steps? Now, maybe in a density boost step, I'm going up like 100 alpha, but that's just a constant. So what would happen if he gives me k times density boost steps, or order k times, then I just won't actually create anything. I'll never make the book. I'll be like someone who saves up their whole life to enjoy themselves, and then I don't know, just suddenly dies and never does anything, right? So that would be exactly what happened. You just save up this density and never use it. So you definitely want that alpha times k is big, because otherwise you could just be slowly increasing the density. I've increased it from 80% to 90%, and that's all I've done in my life. That's no good. And these seem to be contradictory requirements, right? So it seems like we had this very nice story of how we should be maintaining the density, doing red steps, but it all falls down because we can't choose the value of alpha. So here's the solution. Basically, I sometimes say, you should be inspired by your friends who go off and become bankers because they understand how to talk about investments and return on investment and all this kind of stuff. And they'll say, it's gone up by 10%, gone down by 10%. You think of things in percentages of your capital, right? And that's kind of what you want to do here. If your current density is, say, below where you started, you really don't want to lose more density. You want to be doing one of these, I will only accept to lose some epsilon over k, some little multiple of, this should be here. If you have already gone up a lot, then you can accept to lose more each step, right? And so maybe what you accept to lose should be some base, like epsilon over k, plus epsilon times how much you've already gone up. Right? So you're willing to bet epsilon of your total profit so far if you've gone up. Now, this actually means if you try to keep giving you boost steps, then the growth becomes exponential. And so you can only keep giving you boost steps for sort of order log k steps.
Then alpha is the alpha step.
Right. So I said, before I was saying we have to choose alpha as if it was a universal alpha that you use forever. It's not. Before every step, you define an alpha I, which is for step I. So if your current density is small, then you might choose a small alpha I. If your current density is shot up, it's already much bigger, then you choose an alpha I in the step. Thanks. Yeah, it's worth pointing out. And this is usually P minus P0, so the type of it. Okay, so we probably won't do all the details of calculations, but you can basically say, thinking about the way the algorithm is defined, you can work out roughly what is the size of x and y at all steps. Basically, in red steps, you're losing this factor 1 minus gamma, in the blue steps, you're losing a factor like gamma. And when you think about y, you lose that 1 minus gamma in both the red steps and the boost steps. So that's also part of the equation. I think there's maybe a technical detail which I didn't include here because it's obviously simplification for a talk, which is that the boost steps, I put them as a gamma to the S here. The boosts can actually involve going into blue names that are smaller than gamma. And you need to analyze what's the worst case of this, right? So that if you do in detail, you have to work out what's the worst case, but there's a convexity argument. It's not too bad. This enables you, this is related to, if each boost is 100 times bigger than what you go down in a red step, then the number of boosts should only be 100, right? Because if you start doing more than proportional, then the density starts to go up. And if the density starts to go up, you start to get these exponential increases. Basically, you can check the details, but you can say that boosts really should be at most a certain proportion of the red steps. And if you're far off the diagonal, this factor is quite small. And this gives you the win fairly far off the diagonal. How do we get to the diagonal? We do the same approach. Weirdly, we decide on the left not to do blue just if it's at least a half, but if it's at least 2/5. In other words, we accept the lower density of blue on the left to do blue steps. For some reason. What happens is it doesn't work at all. You prove RKK is at most 4.04 to k, which is not very impressive. So what happens is you get to this situation for a certain t, and you want to say you're bigger than the Ramsey number. If you're just using the Ed-or-Sekerish bound for the Ramsey number, then you get that worst bound we just showed you. Except you remember the off-diagonal result has already enabled you to improve this Ramsey number. So using the improvement you already have, then you can get a result. And behold the disjoint failure sets, you can basically think it comes down to a two-dimensional picture, depending on how many red steps, how many blue steps you do. And you can plot where you will fail to find the book that's large enough and where you fail to get a blue clique on the left. And it happens in all cases, one of these two things happens. So you either get the red book you wanted, or you get the clique of blue on the left. Breaking news, okay, now from a few months ago, this team from McGill, Gupta, Ndiaye, Norin, and Wei proved 3.8 to decay as an upper bound. They called their paper optimizing our method, the CGMS method. I would say they optimize and adapt it because there's definitely new ideas in there. In particular, for the off-diagonal case, they managed to do it all through an inductive argument, which is based on the number of surplus edges between the two sets. So the vital sort of statistic they look at is not really like current density. It's like how many red edges do you have between two sets in surplus or more than P density. And they managed to write a reduction argument based on that. You know, it would be really great to speak for like, do a whole class just on this, but it's kind of not my current objective, but it's a very nice argument they have, and it's very nice they can improve the bounds.
Do you know how many pages?
I think it's about 20, but I should mention so let's say quickly something about, maybe I'll even, for those on the video, I'll stop sharing. Okay. Right. There you go. They're back in the room. So maybe I'll even say something about the their paper, they also have the final section in which they talk about multicolors, and they can do some free color cases or multicolor cases with their proof that's more similar to an induction argument. But it works if one of the colors you're looking for a clique which is much bigger than the others. In particular, they got an improvement if the sum of all of the other sizes is the most 0.69 of the first. So this doesn't get you close to, if you think about the diagonal case, let's say KKK, then obviously the second and third color would add up to twice as much as the first one. So they got an exponential improvement on the upper bound for this, provided the sum of all the other clique sizes at most 0.69 times the first. Maybe just to finish the next 2 minutes, I want to say even our method for two colors, or all their variations on our method for two colors, why are they difficult to generalize to more colors? And I would actually say there's two questions. Here are two questions which appear to be completely different. Okay? Why is the argument better off diagonal? You know, when L is K over 100 or something. And why is it difficult multicolor? And it's the same reason. And that is, so that for a particular method of building this book in red, and for the particular moment when you're thinking of doing a red step, you have this issue of what boost will I get if I have a bad red density here. So if this is bad, I want to get density boost with the rest. Now, at that moment, I said it's useful that this red neighborhood is quite big. Because that was like the majority being a bit bad means the smaller set would be very good. And really that trade-off just works better. It just works better if the red degree is quite big, relatively. Even if they're both the same size, it's not working so great. Well, once you go to 3 colors, then you have to worry about, is the blue degree quite big or is the green degree quite big, right? So in other words, in an extremal-ish coloring, what degree would you expect in red? Well, if you start from the diagonal, you want the red degree being like 1/3. 2 colors going from the diagonal, the red degree is like 1/2 or something. Maybe you can change the rule in a funny way and make the blue degree a bit smaller, or you know. But in any case, it all is going to become much more difficult computationally if you have to deal with 2 other colors, because then the red degree is probably just like 1/3. And being bad to 1/3 means you're a tiny bit better than the other 2/3. It's all going in the wrong direction, right? The boost would be very unimpressive. And it would just get worse if it was like a 10 color thing. And then the red's just this little bit. In this sense, the method falls apart. So it's somehow not for a philosophical reason. It's almost just like a numerical reason, like this number compared to this number. It just doesn't work so well. So anyway, I hope this description reminds us the importance in these Ramsey things of like building this book structure. And it also shows us that this idea of just making one book in one color runs into problems when you go to multicolor. And I hope this is a good basis to, start from when we come back next week to think about how can we try and make it different. Well, some ideas in common, but quite different argument to try and go multicolor. Okay, so cheers. Well, stop for today.